Hello community! Today we're gonna have fun. We're gonna code a smart intelligent pipeline between our large language model and our retrieval model and our data models. This is part 2. If you've missed part 1, this is the way to go. So you remember we want to have a pipeline for self-configuration, self-learning, self-optimization, and we found out in part 1 that our pipeline representation should be graph-based, and we can use here the graph theory tools and mathematics to optimize our pipeline. Now, what is the problem? Remember React. In React here, synthetic reasoning and acting in large language model. This is here the hard-coded prompt here. This is our React prompt for thought, action, observation. And this is by someone who found this. And it's great. It's a trial and error. And here my colleagues at Stanford University, they analyzed this for different prompt structures. I just showed you here prompt 3, React, with close to 3,900 characters. But look at this from LangChain. We have a prompt for the question and answer with sources. We have here close to 1,000 words hard-coded in the template, and we have 6,200 characters. You want to see this? Here you have your LangChain prompt template, and this is something that we want to optimize. My goodness, but you know why? Because my knowledge domain has a complete different reasoning pattern. I'm in physics, theoretical physics. And if you tell me here something about, I don't know, the Constitution or politics or the news in the US or anything about some contract law, this is nice. But this is not my domain. This is not my knowledge domain. Quantum logic is completely different. This is not valued for me. It's not high performance. So you see why I have a problem here with all this LangChain hard-coded template and everything else. And I tried different template source providers and nothing worked. So today we're going to find a solution. Just think about it. If we have here our LLM in the middle, and then we have here all our data models and databases and vector stores and whatsoever, and our retrieval model, we have a chance. So if we have an intelligent pipeline, it has access to all the external data. And now our intelligent pipeline can use this external data to design a specific training data set. But it can either decide a training data set for PathLore, so we can fine-tune here our LLM with some supervised fine-tuning algorithm from Hugging Face. So we bring the external knowledge back into our LLM, or maybe the intelligent pipeline decides to use the external data to just design a specific training data set for in-context learning for some few-shot example for RAG. This is an interesting thing because in theory, what we want our pipeline to do both. So let's say 50-50 or 30-70 or whatever, 10-90. The pipeline should decide on my task given, on my query given, if to find here the optimal answer, it should use here 10% fine-tuning or a 90% ICL RAG training dataset creation. This is the problem we are facing today. So, but you suddenly understand that this intelligent pipeline now has the possibility to create a dataset. So the pipeline now decide if it should fine-tune our LLM on a generic procedural knowledge, on some generic abilities about some basic complexities, where the data will be fine-tuned, will be brought into the tensor weights of our large language model. So we have an inherent weight representation of this new knowledge, ability, complexity. Or it might decide that for ICL RAG, just for some recent data updates, that it will not bring new updated data sets in because those data are familiar structure. It will just say, hey, via ICL RAG, here's the latest update on this and this parameter. So this is a kind of intelligence I'm looking forward to. We have here January 17th, 2024, Microsoft, a beautiful study. And Microsoft looked in detail now here in January 2024 on pipelines. And pipelines exactly between here our large language model and our retriever. So it is RAG versus fine-tuning. How should we build our pipelines? When does a pipeline decide what to build for what system? It's clear. Let's have a look here what Microsoft writes here. Retrieval augmented generation and fine-tuning. RAG augments the prompt with some external data, while fine-tuning incorporates the additional external knowledge information into the LLM model itself. And there are pros and cons. And I said, hey, we now have a detailed look at this. And we tried out with the Microsoft infrastructure. What is better? RAG, fine-tuning? And what is better? 30-70, 70-30, 50-50. So how we do this? Microsoft did the following. Of course, it had data, so it built a vector representation of the external data. It did the embedding generation and the index construction. And interestingly, although they have the GPT-4 model and all the embeddings, they computed the specific embeddings of the knowledge domain of the data using sentence transformers, using SBERT. And then they had for the retrieval, for the ICL RAG, give them an input question. They, of course, took this question, they computed its specific vector embedding and retrieved then the relevant chunks here in a similarity operation, you know, cosine similarity or any other similarity matrix that you want to apply to. So this is what they did here. Please notice they computed their embeddings. I think this is a beautiful thing to do for be domain-specific, high-performance domain-specific. And for the fine-tuning, Microsoft did the following. It fine-tuned GPT-4. And you say, yeah, of course, they are allowed legally to fine-tune GPT-4 from OpenAI. But they used here just a smaller version here, just a cluster of 7 nodes. Each node had 8 times an A100 GPU. So with just a total of 4.4 terabyte VRAM, for some days they were able to fine-tune this here on this additional external training dataset. So now they had here this data, and they could look at the performance. Now, it is interesting to find here an economic balance, because maybe you, definitely not I, am able here to spin up here 50 or 100 GPUs every time I should have a little bit of a fine-tuning for my GPT-4. So we have to find an economic balance. However, in the research and the pure scientific data format, you have also to decide for your question and answer supervised fine-tuning or the prompt engineering with in-context learning. So what they found. At first I thought it's interesting. Microsoft tells you, hey, due to the complexity and the amount of available data, we did the full-time calculation, but we used here an approximation, here the parameter efficient fine-tuning low-rank LoRa adaptation for the fine-tuning. So come on, Microsoft, you had to do LoRa. You have 100 and 1,000 and 10,000 of GPU and you apply LoRa? Okay, whatsoever. Bene. And they checked out different metrics designed to guide here the quality assessment of their process, the relevance, the global relevance, the coverage. You can read this in detail, beautiful. And here is what they found. They did it on a Llama 2 jet, on a Llama 2, and then the GPT-4 system. Now, the Llama 2 Jet 13B, not fine-tuned, had, for specific test, an accuracy of 76%. If they added an additional RAG, ICL RAG, they dropped from 76 to 75, plus minus 2 error bar, so they stayed about the same. So RAG did bring nothing to the Llama 2. However, when now, unfortunately, they changed the model because they went from a Llama 2 Jet to a Llama 2, also 13B, and then they fine-tuned now the Llama 2. And they said, hey, now with the fine-tuned, additionally fine-tuned, further fine-tuned Llama 2, we go from 76%, we go to 68%. And now, being now at 68%, if I now add RAG, I go to 77%, plus minus 2 error bar. But you see from 75 plus minus 2 and 77 plus minus 2. Yeah, so Microsoft, congratulations. I don't know what you proved, but this is the result. Now, what's interesting is GPT-4. GPT-4, not fine-tuned, has, on this particular Microsoft test, an accuracy of 75. And if you add RAG after the additional fine-tuning with this specific data set, you jump from 75 to 80. Beautiful. But notice, 80 plus minus 4. Okay, whatever. And then we took GPT-4, we fine-tuned it for some days on 4.4 terabyte of VRAM, And now we jumped from 75 to 81%. And then if we applied additionally, after the fine-tuning the RAG, we jumped from 81 to 86. This looks nice in the first glance, but have a look here. If you use the GPT-4 not fine-tuned, just with RAG, you have 80 plus 4. So in one extreme point, it is 84%. And here, GPT-4 fine-tuned plus RAG, you have 86 minus 2, so it is 84 in one extreme point. So you see you have here 84 and here 84. So statistically, it is possible that, yeah, you get it. But of course, Microsoft told us, hey, the GPT-4 fine-tuned plus RAG model provides a detailed answer, making it one of the most accurate and informative models. So Microsoft told us, hey, good news for Microsoft. You should pay here for the GPT-4 by Microsoft. Then you fine-tune your GPT-4 on your Microsoft cloud infrastructure, and then you use the RAG system. No, you pay for the RAG application on the Microsoft cloud infrastructure. So this is a win-win-win situation for Microsoft. Great. So what I want to show you is a real-world example. Get a feeling for this. They did some experiment. They had a question. Hey, what is the main concern of blowing dust from excessively tilled fallow fields in the low precipitation wheat production region of the inland Pacific Northwest? Okay, if you were in the US, you know where's the inland Pacific Northwest and what is the wheat production region over there. I had no idea, but anyway, the reference answer in our data set was soil loss, this is the main concern of the blowing dust, and air quality. So the system should find those two, and you see I've color-coded the answer. No, the real GPT-4, unfine-tuned, unragged, just your normal GPT-4, found a beautiful answer. Air quality, soil erosion, erosion of soil, erosion. Really nice, really informative. Now, let's see, after all, the RAG application by Microsoft here on the Microsoft Cloud. This is the answer. Leads to repeated soil loss, reduced air quality, imposes a health risk when inhaled into lung tissue. You notice that, yeah, we have our two strings, but it is much more condensed, and there's a reason for this. However, look at this. If we just look now at the fine-tuned GPT-4 on this specific data set for agriculture, you see, again, loss of soil organic matter, air pollution, soil disturbances. So it is always there. So maybe this, if Microsoft uses this as a main example, maybe they should have chosen something that GPT-4 did not find, because you see here, even in the naked GPT-4 version, it is evident. So maybe I would have chosen an example that is not able to solve this, and then you can have the RAG and the fine-tune. But look now at the fine-tuned and RAG. After two optimization steps, we get this. And you have loss of soil, soil loss to soil loss, air quality, air quality, air quality. Beautiful. So you see, it is heavily specific. If you do RAG, if you fine-tune it, what you prefer, or if you do both, yes, I know Microsoft will offer this as a commercial service, but I think it's up for you. You have to decide what you want to do. But we go a step further. We want to become a little bit more professional. So we say this is nice, but this is not what we want. We want here to optimize the fine-tuning. We want an automatic optimization of ICL RAG system, and we want a structural optimization of the pipeline. So we want that the pipeline itself as a graph structure optimizes its and finds its optimal graph node edge configuration in a mathematical space. Plus, we want that both modules here optimize inside the model. This is now the step we're going to take beyond everything else that you know. And this here, Stanford University, UC Berkeley, Microsoft, Carnegie Mellon University, and Amazon work together. And here, October 2023, they had now DSPy. This is part 2 of a video series, and in the first video series I showed you DSP. And now Pi here is for PyTorch. And you understand that now we are coding this. So we are compiling some declarative language model calls into self-improving pipeline, and you get it, we code it in PyTorch. So this is the background. We want to optimize each component of our I pipeline and the complete I pipeline as a graph structure, as a graph representation itself. Easy peasy. And here is here. This is DSPy, as seen by my GPT-4 system. We have now a significant shift from a traditional language model pipeline implementation, either to a retrieval model, external data, or whatever, which relied heavily on hard-coded prompt templates. And now we change the game. We go towards a more systematic, a more modular, and an optimized strategy without any hard-coded templates. Stanford introduces here 3 elements: signatures, modules, and teleprompters. Teleprompters is a little bit strange if you know the French, but I read that they were thinking about prompt generation. So prompters was the prompt generation, and tele was for from far away. So teleprompters in their idea meant to generate a prompt from far away, and teleprompters is not what the US presidential candidate use when they give a speech. But teleprompter means here something completely different. Beautiful. In my words, what is a signature? Signature is something to abstract your prompt. A module is to abstract the prompting technique, and a teleprompter is simply an optimizer for when you chain here the models together, that the whole system is optimized. You know this from our fine-tuning. If you have an Adam optimizer, more or less the same thing, different level. Okay, with those 3 elements, we can now do a programmable, intelligent pipeline function. The goal is to help researcher and practitioner build new language model pipelines quickly and achieve very high quality through automatic compilation, through self-improvement, instead of manual prompt engineering, instead of LangChain hard-coded prompt templates, because they are never on the domain that I need them. In contrast, Stanford writes, typical existing research implementation and existing libraries like LangChain or Llama Index are implementing using manual prompt engineering, which is the key problem that this methodology tackles. Beautiful. Now, let's look at all those 3 elements in detail. A signature is a natural language type declaration of a function. A short declarative spec that tells you the program what a text transformation needs to do. Consume a question and return an answer is the easiest one that you know. Normally, it is a tuple of input field and output field and an optional instruction. If you remember this, you are fine. Signature is a tuple, input field, output field, plus additional meta instruction. Field consists of a field name, metadata. Yes, you can read this. However, what is nice, the signature offers a benefit over the prompts. The hard-coded human-written prompts, they can be compiled into self-improving and pipeline adaptive prompts, or even fine-tune a complete LLM system. And this is done by bootstrapping useful demonstration example for each signature. If this sentence tells you nothing, have a look at part 1 of this video. So, what is a signature? Here we have it. Question to answer, or long document to summary, or context, question, create the rationale and give an answer, or a lot of passage text, extract the main entities. Those are signatures in our coding. Next one, modules. Module you will always find here is the predict module. The core model for working with signatures in DSPy is predict. Predict stores the supply signature, an optimal large language model to use, GPT-4 or whatever you have, or even an open source model, and a list of demonstrations for prompting. See part 1 of this video. They build it like layers in PyTorch when we build neural network structure on our transformer network, So this instantiated model behaves as a callable function. It takes in the keyword arguments corresponding to the signature input fields, for example, question. It formats a prompt to implement the signature, and it includes the appropriate demonstration, calls the language model, and parses the output fields. And when you use it then in the compilation mode, it will also internally track input-output traces to assist the teleprompter at bootstrapping the demonstration files. What is a typical module Jupyter counter? DSPy chain of sort, DSPy program of sort, DSPy multiple chain comparison, or DSPy React. React started my video today. They all can be used interchangeably to implement here a DSPy signature. And now the beautiful thing of those modules is, here's the predict module for you if you want an pseudocode to understand it easily. Those DSPy models can be composed like Lego bricks. You can build beautiful things with them in an arbitrary pipeline in a define by run interface. So inspired by PyTorch, and yes, we have here a simple illustration. And this here is now the complete self-optimizing retrieval augmented generation, our RAG system in DSPy. We define here the class RAG, a module, initialization, and the forward structure. And here in the forward structure, you can build whatever you like with your different modules. Simplest case you see here for the RAG system. But we can go beyond automated RAG optimization. Third element is teleprompters. Teleprompters can augment prompting for arbitrary pipelines. So when we compile now a DSPy PyTorch program, we generally invoke here a teleprompter, which is an optimizer that takes a program, a training data set, and a specific quality metric, and returns a new optimized program. You know this from fine-tuning. In fine-tuning, normally we have an LLM, we have an Adam optimizer, and then we do here the training, we compile it with a specific training data set and a quality metric. This is here the same with DSPy. We may compile here the RAG module from above against a dataset of question-answer pairs. This is our training dataset, and we give here specific metric. The metric is easy, the exact match with a test training dataset. The goal of the optimization is to effectively bootstrap here some few short demonstration. Have a look at video number 1 if you want to know what this is. I showed you there in detail. And the code for all of this here is this. We have here our DSPy example. So a question and an answer. What is the capital of France? And the answer is Paris. And you say a one-shot example that is amazing. I know, thank you. And then our teleprompter will bootstrap here the missing labels, the reasoning chain, our chain of sorts, and the retrieval context. And I show you later on an example. I go with you step by step, just that you see now the complete program. You have a DSPy bootstrap few-shot with a metric that is defined. And then with a teleprompter, we compile now the RAG function we just defined before on a training data set. As easy as these 3 lines of code. So the bootstrap few-shot teleprompter simulates here the RAG on the training example. It will collect multiple demonstrations on each module, example of input-output behavior, that collectively lead to a valid output. Great. Now we have it. If you want to see here the class here of the bootstrap few-shot, this is it. There's even bootstrap few-shot with a random search functionality. This is it. And then we just have left the compiler. And then that's it. This is all that we need for DSPy programming. So here we go. Key source, DSPy's expressive power is its ability to compile or automatically optimize here, not just here the chain of the modules in the graph structure, but also each model in itself. Compiling relies on a teleprompter, as I just showed you, which is, again, an optimizer for the DSPy programs that improve the quality of modules via prompting. So we have here prompt engineering, ICL RAG structures, or and this is the second really interesting thing, I will do another video on this. This now starts to fine-tune our large language model automatically. And it finds the perfect balance between prompt optimization, ICL, RAG, and fine-tuning. Unified in DSPy. How does the compiler work? If you enter this compiler, step 1, step 2, step 3. Beautiful. And here we are, a summary. This was it. It was so easy. Now, just again. DSPy introduces a programming model that abstracts here our large language model pipelines from the LLM to the external data, to the retrieval model, to the external data stores as a text transformation graph structure. This model views here the language model as modular components in a computational graph. We have all the mathematicals and computational tools of graph theory that we put on, where each node in our graph represents a distinct text transformation task, like answering a question, Q&A, or please summarize this text. And the optimization is done automatically. The DSPy models are designed to be task adaptive, similar to a neural network layer, but now for the text transformation. So these models now, as I showed you, the chain of thought, and I will show you this in an example in a minute, learn their behavior iteratively. And they incorporate techniques like prompt optimization, fine-tuning the language model, augment the training data, and a reasoning path. We use here in DSPy Teleprompter simply for optimization. Can be sort of a meta-programming tool that guide how models should learn from data, allowing here for an automatic mapping of declarative models to a high-quality prompt composition. So the machine builds our optimal prompt. We don't have to hard code any template. We don't have to do anything about prompt design. The machine will find the optimal prompt design with an optimization procedure. Yes, beautiful. I know this. Thank you. And key feature is the compiler optimizes any pipeline to maximize to a given metric. As I showed you in the test data set, maybe exact matching, or you go whatever you like. Compiler adapts the pipeline by simulating various versions on training inputs, bootstrapping demonstration traces, see video number 1, for self-improvement of the graph representation, and constructing effective few-shot prompts for ICL RAG, or fine-tuning smaller language model for different pipeline steps. An impressive self-adaptive, self-regulating, self-optimizing framework. You just have to give it the modules. It will find a graph structure that works best. You give it some training data set. You give it an evaluation data set. And a little bit of time and quite some compute power. And the model now will, the DSP structure, the programming structure, will find the optimal prompt configuration or an optimal fine-tuning configuration. What is the easiest example I can give you in this? Here. My input is 3534. I have nothing else except 3534. How does the system work? This is just the simplest demo I can think of. So there's no human drafted prompt or prompt template in the background, no LangChain at all. The system must find here the function between them, the relation between them. So it's just a sequence of 3 integers as an input. And the task I tell now the system, generate the optimal prompt engineering, for this mathematical operation. And to show you here, absolute transparent, I do this here in my GPT-4, not in DSPy, but I type some analogon to the DSPy commands because I wanted you to see this. You get a feeling for this, what's happening here under the hood. So I say GPT-4, great. Now I give you a set of numbers, 3, 5, 34, and your task is to find a mathematical operation for this set. Go step by step for your logical reasoning. This is our DSPy model, chain of thought, but this is the sentence for this. And now GPT comes back and says, okay, this is the number, step by step logical reasoning. Yes, yes, yes. So it says, suggesting that the operation might involve multiplication or exponentiation, rather than just addition or subtraction, given the size of it. Then they test some simple arithmetic operation, addition, subtraction, multiplication, division. No, nothing works. Then it's considering exponentiation and combination of the operation. And hey, what a coincidence, huh? This is what works. And then it says, hey, concluding the operation, we found that the mathematical expression would be a squared plus b squared equals c. And this is here the mathematical formula, the reasoning. And I just give it this input, no label, no nothing. And it found here the mathematical operation for this expression. Now make it more complex. Do not give it integer, give it facts, give it relations, give it functions. This LLM really has some functionality we can use here. So you see, that's nice. So GPT-4 finds a beautiful rationale from our LLM. The rationale is, hey, I found a squared plus b squared equals c is the mathematical operation for your input data. Chain of thought, yes. But also look now at the signature. I had a question, 3534, no label, no instruction, no template, nothing to find it. And now I get a question back. I have here the rationale. The rationale is here this mathematical equation. And the answer is that this solves here this input structure. So this is now my signature. And this extended signature, see video part 1, is now my new prompt for the next step and the next step. And you see how we combine syntactic training data that are within my knowledge domain and that are specific to my task, complementary to whatever else. So we bootstrap, okay, sorry, typo. So we bootstrap new syntactic domain-specific data. No, not we, GPT-4 does it for us. Nice. You can go now the other way around and say, hey, can you find other mathematical operation except a squared plus b squared? And GPT-4 goes there and said, hey, I try factorials, I try logarithmic, I try exponential function, I try a polynomial equation, I try a combination of arithmetic with power or the root function, I try here model arithmetic trigonometric function. And it goes through and says, hey, sorry, I could not find it. But this is now new context. This is now new data that you can say, hey, this does not work for you. Imagine you have data from a sensor. And this sensor is measuring a field. And this field has this particular, equation here. So all the data that will come in will follow here this, if you want, this field equation under, So we found here a method that it can interpret all other input data that come from the sensor. Or it can then find, if it has a large enough set of numerical parameters, some other mathematical distribution. So this is here, this bootstrapping of some additional training data gives us an insight here into the logic. Beautiful. Yeah. What is the chain of thought module here? Very easy. This is the definition. We have here the class chain of thought. We have here 2 models, here the initialization, where we just have an output field and a signature, but this is easier is here, the green one. We modify the signature from input, output, to input, to give me the rationale for the output. So we do not need here, this line here substitutes the complete hard-coded prompt templates from LangChain. Because we tell the system, hey, I give you an input, I give you an output, and you find the rationale. And no template structure, nothing. Do it yourself. You are intelligent. You are an artificial intelligence system. Hint, it does not work with smaller models. It does not work with a Llama 2 13B. It does not work partly with a G34B. You need huge models, GPT-4 Turbo something, that it really works on mathematical reasoning steps or logical reasoning steps. Those smaller models below 30, 40 is really problematic. You have to test it out before you do it. You have the predict module, and then you have a simple forward function. Let me show you DSPy in a simplified version on ChatGPT-4. So let's do a one-shot in-context learning. I say, give me a simple question and an answer, a pair. GPT comes back, says, what is the primary function of photosynthesis in plants? And the answer is to convert light energy into chemical energy. Provides here the energy from the sun to synthesize glucose from carbon dioxide and water. Photosynthesis also releases oxygen as a byproduct. Beautiful. Now we create here additional synthetic valuable information. Let's see how we do this. I say, hey, I give you now a question and an answer, so a question-answer pair. Please generate a reasoning pattern, like in chain of thought, to go from the question to the given answer, going step by step for logic reasoning. We will add your reasoning information to the pure question-answer tuple and create a triplet. Start now and give me 3 reasoning informations. Now I forgot to add here the question or the answer. Okay, no problem, so I did it. And ChatGPT comes back and says, hey, reasoning pattern here, energy conservation, chemical process, and oxygen release. Beautiful. We have 3 additional patterns. And I say, yeah, but I don't want 3 reasoning steps, but 3 reasoning pathways you can find for the given answer to the given query. So I want you to generate a multitude of information, different pathways, that we can add in the next step to be more precise for the next related question. And GPT-4 comes back and says, hey, I understood it. So to generate diverse reasoning pathways leading to the understanding of the primary function of photosynthesis in plants, we will explore different angles, different perspectives and aspects of the process. And now we start, now we're in the game. This is exactly what we want here. Self-generated additional synthetic information created or generated by the large language model. So it starts here. Biological energy cycle pathways. All living organisms requiring energy to perform life processes. Plants cannot consume the energy here by eating something. They must produce their own energy, and the photosynthesis is the method. Great. Ecological balance and atmosphere and composition pathways. So I tell GPT, hey, now transform your detailed answer in 3 triplets. With the generic structure, we have a query. Then we have this additional reasoning information that GPT-4 created, and then always the same answer. Now give me your answer in the form of 3 triplets. Okay, GPT-4 comes back, doesn't like parentheses, no problem. So we have triplet 1, but we have always the same query, and we have always the same answer. But now the additional reasoning pathways are different because now we have different perspective how we look at the problem. So triplet 2, and here this is now a different view, and triplet 3, and now we have a different view here. Beautiful. And now I say, hey, you are intelligent, you are GPT-4. Can you add 2 additional triplets? Did you understood, oh yeah, oh my goodness. Did you understood the method how to build them? And GPT-4 says, hey, buddy, absolutely. I understand the method for constructing these triplets. Each triplet comprises the original query, followed by additional reasoning information providing a unique perspective or a unique context, and concludes given the answer. 2 more triplets, and it comes back here for energy transfer in the ecosystem. Interesting. And impacts as a global carbon cycle, absorbing carbon dioxide, major greenhouse gas, play a significant role in moderating climate change. Somehow similar what we already had from the chemical perspective, but now here for climate change perspective. And I say, hey, perfect. And GPT-4 smiles and says, hey, I'm glad to hear that. And I say, come on, but now all those 5 triplets are the input text to answer now the next query. And my next query is related in a similar domain. Why is the light of the sun so important on Earth? And you might say, wow, that's a complicated question. Yes, because it is a simple example, a demo for you. And I say, so we form an identical duplet. Oh, it's a triplet. So we have the question, the new question. Then we have 5 triplet from the last answer. where we have this chain of sort argumentation. And then I'm looking here for my new answer to my new question, given that I already had in the last question 5 chain of sort additional information blocks. And even if I was wrong here that this is not a duplet but a triplet, GPT-4 says, hey, I understand the task. To address the new query, why is the light of the sun so important on Earth? Using the information from the 5 triplets related to photosynthesis, we can create a duplex structure that integrates a new question with insights drawn from the previous triplets, leading to a comprehensive answer. Let's proceed now. So the query is, why is the light of the sun so important on Earth? Integration of insights from previous triplets. Beautiful, GPT-4. That's the way to go. So we have now 1, 2, 3, 4, 5, exactly what we already had. And then we have a new answer to our new question. And now I say, hey, did you use all 5 additional informations, or did you focus on a particular triplet only from the last 5 triplets given in the last answer? And GPT-4 comes back, hey, in my response, I integrated insights from all 5 of the previous provided triplets, each offering a unique perspective on the importance of photosynthesis and the role of sunlight in various ecological and biological processes. Here's a recap showing how each triplet's additional information contributed to the new answer. And it comes back and says here, really, so from triplet 1, triplet 2, triplet 3, triplet 4, triplet 5, shows exactly here. Lastly, the global carbon cycle pathway, the triplet 5, brought in the viewpoint of how sunlight through the process of photosynthesis impacts global change by enabling plants to absorb carbon dioxide, thereby acting as a natural carbon sink for our global carbon cycle, the planetary carbon cycle. So you see, in summary, each triplet's additional information was used to construct a comprehensive answer to the new query, demonstrating the multifaceted importance of sunlight on Earth, particularly in its role in photosynthesis. So you see the LLM generated additional synthetic data, but in a way and form that we can now say, listen, go run for yourself, self-create now, 100, 500 different perspectives. And in this, find here maybe the chain of thought, a logical reasoning pathways, however you define this. If you have 500 different runs here, you can be sure that somewhere there is the right logical pathway to your problem. And now you can say, hey, the next step, why not evaluate here the importance of each of those 5 additional information blocks for you for answering this particular query. So you see, it is beautiful here. This was just here a very short demo. What here the class from DSPy on chain of thought, what it creates, how it operates, what it synthesizes here on new additional data from the knowledge domain by our LLM, and how we can integrate this new information and get a much more richer information reply that now the LLM is feeding itself the information in a reasoning cycle, maybe in a chain of thought argumentation or in a specific logical pathways that we can define now in a second example, because remember, I just showed you here that we did this in a one-shot example. So we only had here the very first question, and this was, hey, what is the primary function of photosynthesis in plants? And only one demo answer. And if you have now a more complex, maybe complementary structure in your 5 or 10 question and answer pairs that you give as a pre-training dataset for the optimization project, and then you let it run for, some hours, I think the data you generate on this particular question, on this domain-specific question, we get now a lot of additional information that will help us to answer all the questions about this particular domain. This was it for this particular demonstration. I hope you enjoyed it. So here we are in a Jupyter notebook, and we are here now in the official DSPy tutorial at SkyCamp. So I just run through this with you. I give you the link, you can download the program, you can experience it yourself. So where are we? Here we have now to define our LLM, and we go here with a Llama 2 13B jet from Hugging Face. And for our RAG system, we have now Colbert version 2, where is here the Wikipedia abstracts. Great. Still downloading. Yeah, take some time. This is a free Colab notebook, a T4, so you don't have to pay anything. Nothing at all. Satisfied? Yes, come on, baby, show me. My goodness, this takes time. Okay, we can continue. So this is now our system defined. And then we say, hey, DSPy settings configure. Our retrieval model is Colbert version 2, and our large language model is a Llama 2. Beautiful. Now here, the training data set. As I told you, we do not have a template structure in the background, but we have here, let's say, a one-shot example, or a three-shot example, or a five-shot example, or in this case, a seven-shot example. This is the official notebook by DSPy, so I just show you what they did. So you have a question, who was the director of the movie feature? Yes, and then you have an answer. And what was the year of the, yeah, and then you see a very simple logical structure to follow here. We see this is the training data set, beautiful. And then for the evaluation, we have here an evaluation data set, beautiful. Now, we have now a simple predict function. So we say DSPy predict, question, answer. Couldn't be easier. We have no chain of thought for the moment, comes up later. And we say, hey, a zero-shot question and answer, how good are you? Am I done? Yes, done. So next one. Come on. Llama 2 and Colbert. Done. Beautiful. The training data set. And here we go now. Yeps. And so you see here to predict, the question is, what is the capital of Germany? Answer, Berlin. Beautiful. But if you want to find out what happened, you just say inspect the history of your LLM. And then you have here the structure. You have given the field question and answer, and question should produce here the field answer. And we have the following format, zero shot, so just question answer. Question, what is the capital of Germany? Answer, Berlin. Now we do this with it, the simplest chain of thought. This is not the real chain of thought, this is a simplification, as you can see. So we define now the class COT, a module, as you can see, and we say DSPy, chain of thought. This is a predefined question answer. Beautiful, let's do this. And then we say we have here a special metric. The metric is please do an exact match. And then, as I told you, we need here a teleprompter. The teleprompter is here, I use here the Bootstrap view shot. I showed you the formal for this. The metric I have is exact match. Bootstrap demos is, let's go to 2. And then I have the compiled version is teleprompter.compile, and we compile this chain of thought function, this DSP module, this class, this DSP model on the training data set. Yep, done. Yeah, of course, this is just a demo, so we do not have enough data, but just as a demo. And then we say, okay, what is the capital of Germany? So you have the prediction of the rationale. Now we have additional synthetic data, determine the capital of Germany. We know that the capital of Germany is Berlin. So the answer is Berlin. So this is from the Wikipedia. The answer is Berlin. You are amazed, I know. Yes. So inspect history, the last step, given the field question answer, you have here the training data set. Beautiful. And the format you should follow is here, you have a question. Then we have here the reasoning. Let's think step by step in order to produce the answer, and then you have the answer. Then you have here a training example. What author is English? This one guy or this guy? Okay. And then you have now my question. What is the capital of Germany? Let's think step by step to determine the capital of Germany. We know from Wikipedia that the capital of Germany is Berlin, so the answer is Berlin, answer Berlin. And you say, amazing! But now we do here the evaluation on the evaluation data set. And then let's see what it is. Oops, here we go. So you see here exactly the question and the example answer that it should be, and then the rationale that but this is a Llama model, so it's much too small to be really functional. So the predicted answer, and then you see the exact match, false or true. And you see there's one true. That's, yeah, a Llama 2 is not able to do this, but for the demonstration, it is a free Llama 2 model. So you go with your model that you like. Maybe take a little bit more training time. Great. So let's do now RAG with query generation. So here we have again the class of the RAG as a DSPy model. You know this. We have the retriever, a query generator, and an answer generator. We have here a chain of thought. I just showed you question, search query. Then we have here another chain of thought from the context, question, generate an answer. Generate query, retrieve, done. Let's do this. Now let's evaluate the next step. And let's compile this. And then we want to, compile, yes, come on, baby, come on. Done, 100%. 11 found, beautiful. Now I want to see if it's better. It's a little bit better, you see? True, 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 true. So, but remember, it's just a Llama 2. This is not the model for logical reasoning. But anyway, you see, it works. Beautiful. Yeah, for one. And then multi-hop retrieval and reasoning. This is from the first part of this video. We can have here the class of a multi-hop as a model. You define how you put your models, for example, the chain of thought model together for a different signature, how you combine your Lego bricks here, how you build your query, your system, your answer. You have here for multi-hop. You see, it is so easy and you do not need a template. It does it for you. This is so nice. You compile it. Yes, yes, yes. In real time, you have a better accuracy. And you inspect it. And then you have here, again, here our evaluation data set. So you see, DSPy, real nice. It is in development. There are some new models coming out. There may be another video I will make here on the advancement of DSPy for particular topics, but you do not need to stick here with the traditional hard-coded human-written prompt templates. Now we have the dynamic generalization, and it is simply mathematical and optimization problem. So why not use a computer and an AI system to do the optimization of the prompt engineering for us? It is a huge step forward. And next time, maybe I'll also show you how this will automatically fine-tune your language model. Would be great to see you in my next video. Until then,